Our next unit is going to be on kinetics and equilibrium, and this lesson is going to be on Le Chatelier's principle. And in this lesson, we are going to look at three things. We're going to look at equations, chemical equations at equilibrium. We're going to look at exothermic and endothermic reactions, and we're going to look at Le Chatelier's principle. So first, exothermic and endothermic reactions. Typically, whenever we have a chemical reaction, energy is consumed by breaking the bonds of the reactants. Energy is released by creating the bonds of the products. And so, if I have something like CO2 right here, that what we have is we have a carbon atom, and it's going to be bonded to an oxygen, double bonded to an oxygen, double bonded to this oxygen here. And so, let's say that if I'm going to decompose this, and so, we're doing our standard decomposition reaction. So CO2 is going to decompose into carbon and oxygen in this case, oxygen gas in this case. I've got to break these bonds that are in here. I've got these nice little double bonds, and they have to be broken in order to be able to do this decomposition reaction. Now that takes energy. And so, as a result, is that there is energy consumed anytime you break apart certain reactants like this, or certain molecules like this, is that those bonds, those connections between the molecules have to take energy to be broken. But likewise, is that if new things reform, that you go from individual pieces and they reform into new molecules, you're also basically given back energy. There's energy released in that. You can almost sort of think of it like having, like maybe like a hill or something like this, is if I'm going this direction, is that we're at the bottom of the hill right now. To get up to the top of the hill, right up here, is it's going to take energy to push yourself all the way up there. That's like the process of basically breaking the molecules apart, breaking the atoms, separating their bonds. But then once you get over the top of the hill and you go down, is that you're going to gain that energy back, at least some of the energy back. Perhaps more than that energy. Depends on whether your hill is one that sort of is low on one side or whether the hill is one where it's high on the other side like this. As you go across in this case, is we are going to gain more energy back than we put into it. And in this case, you're basically going to lose energy because you don't get as much back as what you started with. But this is what happens in most every chemical reaction, is that, there's going to be a difference in total energy because of the fact that it takes energy to break apart the bonds, and it gives you back energy whenever you create new bonds for the products here. So if more energy is released in creating the product bonds than is consumed in breaking the reactant bonds, that would be sort of like this first case we talked about right here, that you get more back than it took to put in the first place. Energy is released in the reaction, and this is called an exothermic reaction. Exo means outside. And so if you do a chemical reaction and it basically gets warmer, this is a very good indication that this is an exothermic reaction, because what's happening is it took some energy to break the bonds, but whenever the new products formed, is it released more energy than what you had to put in there in the first place. Now, the opposite of that is also possible. If more energy is consumed in breaking the reactant bonds than is released by them when you create the new product bonds, energy is absorbed. And this reaction is endothermic. Endothermic reactions are typically going to get colder as you do them. And so that would be sort of the example we had right here, where it takes a lot of energy to break these things apart, but then whenever you put them into the new products, they release some energy, but not a whole lot, not as much as what it took to put in there in the first place. And so that's an endothermic reaction right there. So exothermic reactions are going to give off heat. Endothermic reactions are going to take in heat. So looking at some examples, well, let's go forward a little bit. We'll get to some more examples of this in a little bit. Equations at equilibrium. Chemical reactions. Every one that we've seen so far in this class have been one-way equations. So we have H2CO3. Carbonic acid decomposes into water and carbon dioxide. This goes one way, from carbonic acid to water and carbon dioxide. Oftentimes, though, in real chemical systems, the reaction can go both ways. Can carbonic acid decompose into water and carbon dioxide? Yes. But sometimes water and carbon dioxide will basically use a synthesis reaction going back the other way and reform carbonic acid. This is basically what happens in pop. You take a sealed pop, it has carbonic acid in it. It also has some water and some carbon dioxide that are in there. If you shake it up, it's going to move the reaction from carbonic acid into water and carbon dioxide. But if you let it sit for a while, that's going to go back the other direction, and some of that water and carbon dioxide is going to form carbonic acid. So this is a two-way reaction. The reaction can occur from both left to right and from right to left. Typically, this will continue until the reaction reaches equilibrium. There's a point where there's a balance between the reactants on both sides. And so eventually we'll get to the point where, we have a balance between H2CO3 and water and carbon dioxide. Doesn't necessarily mean they're going to be equal. In fact, usually they're not. But they are going to reach a balancing point if we don't change any other conditions on the system. And so this is called equilibrium whenever they reach this point. So let's move on this. As we said, this equilibrium does not necessarily mean the concentration of reactants on either side are equal. You could have a case where equilibrium means that there's a whole lot of the stuff on the left and not much on the right. Or vice versa. There's a whole lot of stuff on the right and not much stuff on the left. So generally, any reaction you're going to have is going to favor one side or the other. It's going to favor the left, it's going to favor the right. And in a way to show which side is favored, we use something called an equilibrium constant. An equilibrium constant, the symbol is KEQ. K, little k, big K, capital K, and then a subscript EQ like that. And so this is our symbol for equilibrium constant. An equilibrium constant is going to be just that, a constant for any particular reaction at any given temperature. And so you could change KEQ if you change the reactants or the products, and you could change KEQ if you change the temperature. Other than that, KEQ is, for all intents and purposes, for an ideal gas, going to be constant. It's going to stay the same. Now, here's what KEQ tells you. If KEQ is very large, you get a very large number, like several hundred or several thousand. That means the reaction is going to favor the right side. You're going to have more concentration on the right side, higher concentrations on the right side than you will on the left. That basically indicates a large KEQ. So when KEQ is big, you get going to the right. On the other hand, if KEQ is small, the reaction is going to favor the left side. And so if KEQ is small, then it's going to typically have more concentration on the left than it does on the right. When we say small, we're basically meaning a small decimal. Okay? KEQ does always have to be positive. Now, if KEQ is near 1, then that means the reaction is somewhat balanced between the two sides. Even if you add something like a KEQ of something like 6 or 8 or 0.2 or something like that, we consider those to be near 1. And so it's considered a relatively balanced equation, a relatively balanced reaction in terms of the concentrations here. And so that tells you, by looking at KEQ, about whether or not you have a reaction that's going to favor the right or favor the left. If it favors the right side over here, KEQ is large. If it favors the left, KEQ is small. All right. Onward we go. Whoops, too far. All right. So let's look at exothermic and endothermic reactions with respect to this. Reactions are indicated as being exothermic when you write them out the chemical formula by what's called the enthalpy change. Enthalpy change symbol is delta H. Delta, of course, means change. H is your enthalpy. So the enthalpy change is delta H. Its units are going to be kilocalories per mole. And so if you had 1 mole of a substance, it's telling you how many kilocalories of energy are going to be released or consumed during this reaction. So enthalpy change can be written a couple different ways, but we're going to generally write it as a product. So we're going to write it on the right side of the equation over here. So if it's written as a product, so in this particular reaction here, N2 plus 3H2 is a reaction equilibrium with 2 NH3, 2 ammonias here. So if the enthalpy change over here is positive, like this is right here, then the reaction is exothermic. That basically means there is extra energy given off at the end. Now, if on the other hand, this enthalpy change is negative when it's a product, when it's over on the right side like it is right here, if it's negative, that means that the reaction is endothermic. It meant that you had to take away some energy at the very end. So let's look at some examples. H2 plus F2 yields 2HF plus 129.5 kilocalories per mole. In this case, this is a product over here. It's on the right side. We have a positive right here. If it's positive, it means this is going to be exothermic. Okay. On our next one, C2H5OH plus 3O2 yields 2CO2 plus 3H2O plus 339 kilocalories per mole. Once again, we have a positive here. That means we're going to be exothermic again. This is going to give off heat in this reaction. Our last one, 2HI yields H2 plus I2 minus 2.7 kilocalories per mole. We have a negative sign here, and so that means this is going to be an endothermic reaction. Thermic reaction right here. So looking at the enthalpy change is a very quick way, if you have an equation written out, if it does have an enthalpy change on it, to figure out whether it's an exothermic or endothermic reaction. So onward we go again. Le Chatelier's principle. So Le Chatelier, just for information, was a French physicist chemist. Sometimes you will see it with a little hat over the top like this. Typically in English, we've sort of gotten to the point where we've dropped off that little hat to indicate the way of sounding here, but sometimes you will see the hat on top of Le Chatelier's name. But Le Chatelier's principle allows us to predict the effect of a change in the conditions on a reaction at equilibrium. So basically what we have is this. We have some reaction. It is a double react, goes both ways. And so one of our double arrow guys. And this reaction has reached equilibrium. It has an equilibrium constant. Everything is sort of balanced out in terms of that the reaction is no longer really shifting anymore because it's reached equilibrium here. Now we're going to make a change to the system. And we're going to change something about it. And in the process of changing that, it's going to want to get back to equilibrium again. And so how do we figure out what it does? Which way it goes? Well, we use the Chatelier's principle, which states this. The equilibrium of a reaction always shifts to counteract any change to that system. Okay, simpler terms. If I push the reaction one way, it's going to push back the other direction. If I try to increase the concentration on the right side, the reaction is going to respond by increasing the concentration on the left side. If I basically decrease the pressure by letting the gas go into a larger vessel, so the volume is larger. If I decrease the pressure, it's going to want to respond by increasing the pressure. It's going to move the reaction from the left or to the right in order to undo whatever I did to it. So the equilibrium reaction always shifts to counteract a change to the system. It wants to undo anything you do to it. That's Le Chatelier's principle. So, for example, as we said, if we increase the concentration of the products, the equilibrium will shift to decrease the concentration of the products. If we decrease the pressure, the equilibrium will shift to increase the pressure. If we increase the pressure, the equilibrium will shift to decrease the pressure. Now, how that happens, that's what we want to get to next here. But that's Le Chatelier's principle. So let's apply it to concentration right up here. So the concentration, we'll measure this in molarity. And so in this case is moles per liter. Typically we'll be dealing mostly with gases here. They don't necessarily always correspond. These aren't necessarily always going to be gases. This will apply to non-gaseous materials and non-gaseous reactions. But most of the ones that we're going to do here are going to be gases. So the concentration molarity, moles per liter. That's our molarity, same as it was before. Of each substance is indicated by square brackets. And so if I have a bracket around H2CO3, that means the molarity of that H2CO3, of that carbonic acid. So let's say if we were to increase H2CO3, that concentration, according to Le Chatelier, the reaction would shift to decrease H2CO3. This means the reaction below would proceed to the right and would increase H2O and CO2. So we make H2CO3 get bigger. And so what is this reaction going to do? It wants to make H2CO3 get smaller. And so to make it get smaller, this reaction is going to proceed in the right direction, the rightward direction, to make your concentrations of H2O go up, your concentrations of CO2 go up, and your concentration of H2CO3 go down. Now, I want you to notice that this is a reaction here, is that our first arrow right here, I'll sort of draw over it with my green, This right here is what you do to the system. The blue, on the other hand, is how the system reacts to you doing whatever you did to the system. So while I tried to make H2CO3 concentration go up, the system is going to respond by moving to the left and making H2O go up, CO2 go up, and H2CO3 go down. It'll flow from left to right in this case. Okay? Now, if I do the opposite, if I were, instead of increasing the concentration of H2CO3, if I decreased it, then the reaction would shift not to the right, but it would shift to the left so that it would try to undo what I did to it. Because of the fact if I decrease the concentration of H2CO3, it wants to then increase the concentration of H2CO3. And so it's going to move from the right to the left. The thing to remember whenever we talk about this, though, is that in the process of doing this, it is not going to change what KEQ is. The equilibrium constant is going to stay the same even as we change the concentrations of things on both sides. The reaction is going to shift in order to basically bring things back to that equilibrium constant. Because obviously it's the case that if I change one of the things, because we said that it's going to favor the left side or the right side, if I change one of the concentrations, then that's going to sort of knock things off of equilibrium, and so it's going to reshift itself in order to balance that equilibrium constant back out. Now, in our next lesson, we'll talk about exactly how you calculate the equilibrium constant, and then you'll be able to see a little more on why it is that there is no shift in the equilibrium constant when you change concentration. So, let's see. Temperature. In an exothermic reaction, the higher temperature will be on the product side, while in an endothermic reaction, the higher temperature will be on the reactant side. Okay, that's sort of what we said before. If it's exothermic, that means that there is going to be more energy given off than what's basically taken to split the reactants apart in the first place. That means there's extra energy left over, and so the temperature will go up. If you have an endothermic reaction, then the higher temperature will be on the reactant side, not the product side. It's going to get colder whenever you produce new things because of the fact that it needs extra energy. And so it takes more energy to break apart your reactants than you got back when you form the products. So exothermic reactions are going to get warmer. Endothermic reactions are going to get cooler as you go from left to right. Now, let's look at Le Chatelier's principle. If we were to increase the temperature on the reaction that's below here, our carbonic acid decomposition again, Le Chatelier's principle says the reaction would move to decrease its temperature. So if we increase the temperature, Le Chatelier says it's going to try to increase the temperature. So let me make sure I get that right here. It says, I got that backwards. If we increase the temperature, we heat this thing up, it's going to respond by trying to decrease the temperature. And so in this case right here is that I'm going to make it warmer. It wants to respond by making things cooler. And so since this is positive over here, it means this is the hot side right over here. So this is hot. And the other side is going to be cold. Cooler, maybe. Warmer and cooler right over here. And so if I make the temperature go up by putting a flame under it, heating it up in some way, then this reaction is going to shift in order to go from the hot side to the cold side. And so it is going to proceed to the left in this case because it wants to undo what I did to it. I heated it up. It's going to respond by trying to make it cooler, and so it's going to shift to the left. That means that the concentration of H2CO3 is going to go up. The concentrations of H2O and CO2 are going to go down in response. This is sort of how Le Chatelier's principle would work in this case. Now, here's the thing. Unlike the other two cases, whenever I'm talking about Le Chatelier's principle, whenever we're talking about the equilibrium constant, is that with concentration and with pressure, which is what we'll talk about next, the equilibrium constant doesn't change whenever you do something to the system. But that's not true for temperature. With temperature, the equilibrium constant will change. Is that equilibrium constants are given for any particular reaction at a certain temperature. If I heat this system up, it's going to make the reaction want to go to the left side, and so by going to the left side, basically that is, since we said that KQ gets smaller on the left, is it's going to make KEQ go down. And so since the reaction goes to the left, the equilibrium constant would decrease. If we did the opposite, if we cooled down this system, we cooled down this reaction as it goes on, then it's going to mean the reaction is going to want to go the other way, to the right, to increase the temperature. And so in that case, KEQ would increase. This only happens with a change in temperature. And so for all other types of changes we're going to do, that KEQ will stay the same. But whenever we have a change in temperature, is that since the reaction, in this case, we're increasing the temperature, wants to go to the left to undo my increase in temperature, it's going to mean KEQ is going to go down because of the fact that lower KEQs favor the left side, higher KEQs favor the right side. So that's what we've got there. So now we're looking at pressure here. Pressure is caused by the impacts of particles against the surface. And so, if I have my container right here, remember that the pressure fundamentally is caused by the particles sort of running into the surface. As they bounce off, they're going to exert a force on that surface. And as they exert a force on the surface, that force divided by the area of the surface gives us the pressure. So, since pressure is caused by the impact of particles against the surface, a reaction can increase its pressure by moving to the side that has more particles. Because if the side has more particles on it, then there are more impacts hitting the wall, and so as a result, there's going to be a greater pressure. So, if we want to increase the pressure on this reaction below, once again, our carbonic acid reaction, and we have to do this by decreasing the volume. And basically what we're doing here is, we had some gas in some container, and we're going to squeeze it in so that now it's in a smaller container here. Same gas is in here, and this is how we're going to go ahead and increase the pressure here. Just as an aside, is if you increase in other ways, like adding another gas that's not part of the reaction, that's not going to change things. That's not going to change things the way we're going to talk about here. Then your concentrations will stay the same because the partial pressures will stay the same. But if we increase the pressure by changing the volume, so we increase the pressure in the reaction by decreasing its volume, Le Chatelier's principle says that the reaction would move to decrease its pressure in response. Since we increased its pressure, it wants to decrease its pressure. And so, let's take a look at this. So, to decrease its pressure, we want to look at the number of particles on each side. On the left side down here, we have an H2CO3, that's one particle. On the right side, we have an H2O and a CO2, that's two particles. And so, since this reaction wants to undo our increase in pressure, it wants to decrease its pressure, so it's going to move to the side that has fewer impacts, that has fewer particles, so it's going to move to the left. And so that's basically how you're going to see a reaction when we have a change in pressure. If we were going to decrease the pressure by letting the gas expand into a larger volume, then Le Chatelier said the reaction is going to move in order to want to increase its own pressure. And so in that case, it would proceed to the right, because the right side has more particles on it. Now, note that we didn't count the enthalpy change in this. The reason why is because enthalpy change isn't a particle. It's the amount of energy that's released here. So that's basically how we do whenever we're looking at Le Chatelier's principle with pressure. Now, once again, as we said, with concentration, is the reaction and product concentrations will shift so that the equilibrium constant KEQ stays the same. Is that this does not change KEQ when we're talking about pressure. The only thing that can change KEQ is changing the temperature for any given reaction. If we have a different reaction, obviously we'll have a different KEQ. But changes in pressure and changes in concentration don't change the value of KEQ, but the reaction will shift in order to keep KEQ the same. But a change in temperature will let KEQ change at times. In fact, it will change with a change in temperature here. So let's try some of these out. All right. So, Le Chatelier's principle here. We have a reaction, C3H8 plus 5O2 is a double reaction. It can go both forward and backward, from the left to right and right to left, with 4H2O plus 3CO2 plus 530 kilocalories per mole. And so, basically what we're going to try to figure out here is we're going to say if these changes on the left side occur, then what is going to happen to KEQ, to the concentration of C3H8, to the concentration of O2, to the concentration of H2O, and the concentration of CO2. So, first let's look at this. We're going to increase C3H8. And so if we make C3H8 get bigger right over here, then its concentration has gone up. Le Chatelier's principle says the reaction is going to proceed so that it wants to undo what we did. So it's going to make the concentration of C3H8 go down. And so as a result, it's going to go over to this side because it wants to, since we made C3H8 go up, it's going to want to make it go down. So that means that the concentration of C3H8 in response is going to go down. If we made it go up, it's going to respond by trying to go down. The concentration of O2 over here. Well, since this reaction, it's responding by proceeding to the right, that means that the concentration of O2 is going to go down in response. The concentration of H2O and CO2, though, are both going to go up because it's going to that side. Now, our first blank, though, the one I left alone, was KEQ. KEQ, because of the fact we're changing the concentration and not the pressure, is going to stay the same. There's going to be no change in KEQ right here. All right? Now, let's look at what happens if we see an increase in O2. And so let's say that we've got an increase in oxygen here, oxygen concentrations. And so if the concentration of O2 goes up, Le Chatelier's principle says the reaction will move in order to make the concentration of O2 go down. That means it's going to proceed away from O2, and so it's going to shift to the right. If the reaction shifts to the right, that means the concentration of C3H8 is going to go down. The concentration of O2 is going to go down. The concentration of H2O, because it's on the right, that's the direction it's going, is going to go up. And the concentration of CO2 is going to go up. The KEQ, since we're not changing the temperature, it's going to stay the same. These shifts happen to keep KEQ the same. All right, let's look at H2O. And so in this case right here, it tells us that the concentration of H2O is going up. And so Le Chatelier says this is going to respond by trying to make the concentration of H2O go down. And so if the concentration of H2O goes down, it means it's going to want to shift away from the H2O. So it's going to shift to the left. Reactions will proceed to the left. And so if it proceeds to the left, that's going to mean that our concentration of C3H8 is going to go up. Our concentration of O2 is going to go up because it's going in that direction. Our concentration of H2O is going to go down because it's going away from it, and CO2 is going to go down because we're going away from it. KEQ, once again, is going to be the same. And I am getting way off on here. I'm going to try to draw this so that we can keep up with what things I'm drawing here. Like that. There we go. All right, CO2 is our next one. In this case right here, our concentration of CO2 is now going down. And so let's look at what happens with that. If the concentration of CO2 goes down, the response of the reaction is it's going to want to make the concentration of CO2 go up. And if it wants to make the concentration of CO2 go up, the reaction was going to proceed to the right side to make CO2 rise. And so if the reaction proceeds to the right side, that basically means the concentration of C3H8 is going to go down. The concentration of O2 is going to go down. The concentration of H2O and CO2 in response are going to go up. All right? So that's what we have on that. And of course, we went back to our KEQ, which will stay the same again because we have not changed the temperature. Now, in this next case, we're going to raise the temperature. We take our gas at equilibrium for this reaction and we heat it up. Put a flame on it or something. And so in this case, if the temperature goes up, the Chatelier's principle says the reaction is going to move to make the temperature go down. And so that means it's going to go to the cold side. To figure out which side's the cold side, we have to look at the enthalpy change. The enthalpy change over here shows that it is positive, which means that the right side is the warm side. And so since Le Chatelier's here says since we're raising the temperature, it wants to respond by decreasing the temperature, it's going to go to the cold side. And so in order to go to the cold side, this reaction is going to go away from the right, and it's going to go back to the left. And so it's going to go this way. If it does that, that means that the concentration of C3H8 is going to go up. The concentration of O2 is going to go up. The concentration of H2O, though, since it's going from right to left, is going to go down. And the concentration of CO2 is going to go down. Now, KEQ. We said that the only thing that can change KEQ is temperature. And so in this case, because of the fact that the reaction shifts to the left, since KEQ is smaller when it favors the left and larger when it favors the right, since this is favoring the left, it means that KEQ is going to go down in this case. All right? So this is about the only case that we can do. We can change KEQ is by changing the temperature. So that's that one right there. Let's look at what happens if we change the pressure. In this case, we'll change the pressure, as we said before, by changing the volume. We're making the pressure go up, so we're basically compressing this gas. We have a balloon and we're squeezing it that has this reaction going on inside it. So the pressure goes up. Now, let's just go ahead and take care of KEQ to start with here. We don't have a change in temperature here. Since we don't have a change in temperature, KEQ is going to stay constant. That's not going to change. For our next guys here, if the pressure goes up, Le Chatelier's principle says the reaction will move in order to make the pressure go down. And the pressure will go down if there are fewer particles. And so this reaction is going to shift to the side that has fewer particles. And so over on our left-hand side, we have 1 of these and 5 of these for a total of 6. Over on here, on the left side, or the right side, we have 4 of these and 3 of these for a total of 7. And so that means the right side has more particles and will have a higher pressure. The left side has fewer particles and will have a lower pressure. So, since we are raising the pressure, Le Chatelier's principle says the reaction is going to shift in order to lower the pressure. That means that it is going to move to the lower particle side, and so it's going to move to the left. So this reaction will proceed to the left when we change this here. And if it proceeds to the left, that means the concentrations of C3H8 will go up. The concentrations of O2 will go up. The concentrations of H2O and CO2 will both go down, will be the changes on those right there. Okay? Now, our last case. We're going to add H2CO3 to this particular reaction here. Now, if we add H2CO3, one of the things that we know about this is, well, we look at this, we say, well, wait a minute, there's no H2CO3 in this reaction. So what good will that do? Well, we've talked about H2CO3 before. Carbonic acid decomposes into water vapor and carbon dioxide. Okay? And so because of that, if we put in H2CO3, the result is we are going to be adding H2O and we're going to be adding CO2 because the fact this decomposes pretty much immediately. Remember, we actually said this actually is a double reaction here. It does go both ways. So if we do this, the end result is going to be we are going to be increasing the concentration of H2O and increasing the concentration of CO2. And so if we increase the concentration of H2O and CO2, Le Chatelier's principle says this reaction is going to move to undo that, to decrease the concentration of H2O and CO2. And so this reaction is going to move to the left to lower those. If the reaction moves to the left, that basically means that the concentration of C3H8 will go up, the concentration of O2 will go up, the concentration of H2O and CO2 in response are both going to go down, and since I did not change the temperature, KEQ is not going to change.